Okay, welcome back. And now we pass to geometry. So we have a diagram like this. What we'll do well, this we know what it is in geometry, will be d modulus on band G, our main guy on the automorphic side. And then this is now is defined as space of extended Whittaker functions.
Louder.
Louder. All right. So we have this picture and we have this definition, and also we have this splitting into of this guy into a product, and we have those maps. Now we just repeat everything. We adjust everything to geometry. We'll have a Whittaker, extended Whittaker category that will resemble these properties. We'll have some version of this decomposition. We'll have some version of the functors, and we'll ask if these functors are fully faithful or not. And we'll say what we know. So that's the plan. So I'm going to stick to this board and just render everything to geometry. And so render everything to geometry is not an algorithm, it's an art, but in this case it will be obvious, except that at some point we'll hit infinite demodulus of infinite dimensional spaces, and we'll deal with that. So first I have functions on this product. I have to define I have to imagine what the pre-stacks are that reduce to those two sets. Well, one I already suggested. So GA mod GO will become now in geometry the Grassmannian over the run space. Well, the run space is an indication that we were working with the Adels, where the action here is at finitely many points, and the action here is at finitely many points. So now next, well, we can do N of A that appears here, and that also has been discussed. Then in geometry will be the space, the pre-stack of meromorphic N jets. The run space, and that's the guy that is infinite dimensional, wildly. And then we have to find a geometric substitute, a geometric enhancement of the space of characters. So characters on the n of the Adels trivial on n of k. Well, maybe I should say n of k. What's n of k first? This has two versions. Let me use the RAM version that appeared in Nick's talk this morning. So those are rational maps. So maps from x to n that are rational and also lives over the run space. Namely, so those are maps from x minus a bunch of points into n. Great. So now next is this space of characters on n of a trivial on n of k, and that becomes a pre-stack that I also call by the same name. So a pre-stack, I have to tell you what these s points are, and those will become. So again, it's something that lives over the run space. Should probably put run. Maybe I'll forget about it. But so what are the s points of this guy? It's just so a bunch of finite number of points of s points of x, and then actually let me go here for this. It's bigger. So ch run s points is a point of run, so x from s to run. Maybe underline because it's a bunch of points, and then eta I, which is a rational forms, a rational one form, an S family of rational one forms. So it's a global section of omega restricted to xs minus x. So let me explain a little bit. So where I is for any that corresponds to any simple root. So you have a bunch of those. So what am I doing? I'm just setting this to be the space of S families of rational one forms. So that's here that I'm changing a little bit from what I was doing in number theory, where I chose a one form in order to define the residue. Here I'm letting it vary. And I have R of those according to each root space, simple root space. So that what's nice about it is that I have an evaluation between this pre-stack and the stack of meromorphic N jets that I'm trying to explain how this evaluation here. So I have an evaluation N jets over the run space, fiber product over the run space of this guy, characters over the run space, and that simply goes to G of A, the additive group. No run, nothing. Let me explain this map. So this map, so let's do it. We do it first for GL2, and then it will be obvious how to do the rest. So what is it for GL2? So what's an S point of jets N? It's, so I have to describe this map for any S points. So that's jets of GA. What's jets of GA? Well, that's S points of it are just finite number of S points of the curve, and F, a function on the puncture disk at those points. And that's according to the definition. Just I'm mapping this guy to G of A, to GA. Great, and then what's an element here? It's again the same bunch of points because I'm over the run space, and then in the case for GL2, that's just one family of rational one forms. I just call eta. And so I want to produce now a function on S. So I want to produce a function on S. What do? Just do the residue thing, what I was doing before. I have a function on the puncture disk. I have a one form. So let me say explicitly what it is. So eta, it was there, it's just an element of omega x box OS restricted to the complement of those points, x. So what can I do? I just multiply them together, Fn, multiply them together, and I take the residue relative to S, and that's just a function on S, aka an S point of GA.
What is it? How do you define?
So maybe let me explain. So, okay, so you have this function in O of the puncture disk, right? I want to quotient it down to O of the puncture disk modulo O of the disk, and I can write this conveniently as O of x box time O of s, but with a divisor at x. Yeah. modulo this, that would be the same. Then when I multiply by eta, I go into omega x s, and for that, and that you take the residue relative to s. So just think about the picture. So for each point of s, you have.
Yeah. I mean, my only observation is that before you looked at generic objects which you didn't want to have a divisor. Now
I really do. That's a very good point. I really want to have a divisor. I really want. In other words, in order to define this map, this evaluation map, I need to have the RAM version of jets or of this, not the generic version I was saying with a domain and so on. I need it for here, just to define this, and then I will move back to the generic thing. But it's in the notes. There is an evil remark we discussed with Dennis, and then he said, put it back, erase it. The distinction between the RAM version and generic versions can be adapted later, but right now I do need the RAM version in order to define this.
Aren't they just regular jets of G? Why do you have function on the function disk then?
What are so meromorphic?
Okay.
Sorry, thank you. I put it. Oh, thank you. Maybe I said it the first time and then I erased. Thanks for correcting. So we have that. Now we can form the first kind of convoluted construction, which is because I go back to my cover board, I need to formulate this kind of equivariance. And for that, in the world of categories or in the world of sheaves, D modules, I need to do what I do next. So let's take D modules on the Grassmannian G run times run CH run. That's okay to define everything is of infinite type, or at least on any power of the curve. And now let's take equivariance with respect to meromorphic jets of n over the run space. I hate to put runs everywhere, but that's what I got doing against the evaluation. So let me say it in words. Those are D modules on this product that are equivariant for this group against the evaluation.
Sorry?
I'm just saying it. Oh, thank you. So you do for GL2, and then for any G, you do root space, simple root space by simple root space. So you get a bunch of functions. How many? Just R, and sum them. Should I say it again? So that's the computation for GL2. That's where the content is. And now for any G, you reduce to this situation on each root space. You end up with a bunch of. You do this. You end up with a bunch of functions on S. Sum them up, and you get your result. All right. So I'm trying to define this beast. So let me say informally, perhaps, what it is. So let me say first what it is without the evaluation. That we know, modulo infinite dimensional stuff. So those are, let's say informally, those are sheaves M on this product, on this category. Such that when you pull back by the action of the meromorphic jets on this, you get, well, omega on the meromorphic jets box times M. That would be the definition roughly for without the evaluation, and then you can formalize this as a totalization of a co-simplicial category. But now I need to insert the evaluation, which is what gives me the equivariance with respect to the character. And so then here, the definition will change. Sorry? Oh, well, you can write it as projection on M, where projection is you have the product 1, 2, and 3, and you project to 1 and 2. Right now, the definition will change. I will still have this thing, but I will tensor up with something else. I'll write it and then I explain. Here is where the exponential that I had forgotten from number theory comes in. And it comes in the form of a D module now. So that's what the definition is. Let me explain. So let me first say what the exponential is. Exponential is a D module on GA with the property that if you pull back along the multiplication on GA, you get the box time of exponential with itself. And if a definition is just mimic what exponential functions are in terms of differential equations. So you just take all differential operators on GA and mod out by the relation of the differential equation of the exponential. When you differentiate, you do nothing. That's the definition, and that's a shift theoretical rephrasement of the homomorphism property of the exponential.
So is this a full subcategory?
Great, very good question. It happens to be. So it's not in general. If you even for finite group, when you take invariant, as we discussed yesterday, you won't get a subcategory of the original category. But now this entire block is a subcategory of this essentially because this n is contractible. But it boils down to that.
So do you claim that such isomorphism is unique if it exists?
Yeah, so what you should say in general, well, so first of all, there is a definition in terms of co-simplicial category. Right? So I can write it down if there is need. But, so what you say in words, you say, so again, already informally, you say you take an object here such that when you pull back, you get this, and then it satisfies a higher hierarchy of higher compatibilities according to the co-cycle condition that comes from what's the associativity of the action, and here you need also the associativity of this guy that actually boils down to this. And in this case, this turns out to be a subcategory, full subcategory of the original thing. So I know that this is hard to parse. I can answer more questions. I can write what's the co-simplicial category. So all I'm doing, if you don't want to think too hard, is I'm up here in my reformulation. I define D modules on here, satisfying this thing. And now I have to move to the second requirement, and that's going to be a little crazy. So we go here. All right, so what do I need to do in the hidden board? So far I have this. Let me rewrite it. in number theory, there was this. And now I need to quotient out by T of k that acts diagonally, right? And also, what I'll do three things. First of all, I can always quotient out by n of k because everything will be invariant with respect to n of a according to the character, but the character vanishes on n of k, so I can do that. And then I quotient out by k. So that's, I point out to the note, that's remark 4.7 for the notes of this talk. So let me write down the answer, then we can discuss perhaps, if there is interest. So I want to define a pre-stack which is supposed to mimic this quotient. And so a notation for this would be band G with, so the honest notation for this would be band G with n omega times center of m, sorry, yeah, we'll just the one at the center. Generic extended, but I'll just write for the purpose of this lecture qx. So pre-stack what are its s points are, again it lives over the, but now it's generic, so it doesn't live over the round space. So it will be a G bundle as always, a domain, so something we discussed last time, a domain U. Then I will have a beta B is a reduction, a B reduction of PG on U. So let me write explicitly what it is. A reduction is an isomorphism between this guy and some B bundle on U induced to a G bundle, the induction of some B bundle to a G bundle. And then what I have is I have a bunch of gamma I. How many? For I going from 1 to R. So this is going to be something on U. So if I have a B bundle, I also have an induced T bundle by just dividing by n, and I want this to map to omega x OS restricted on U. Let me write omega x restricted on U. Some unambiguous. And then I mod out by an equivalence relation, which is what the same philosophy we discussed last time, when you are allowed to restrict over a smaller domain and the same datum will. Yes?
Do you want character of BTU, the alpha A character? Or?
Character, oh, great. So that's, yes, exactly, so I forgot. So for any I have a simple root, and I take PTU, and then I cook up a line bundle out of the character and this T bundle, and I want this map all line bundles. Great, thanks.
Naive point of view, but why it's B and not N?
Great. So it's B and not N because if it's actually why is it N omega? Because so why is it? So what's the extended part of this definition is that these maps are allowed to be any maps, not necessarily isomorphisms. Okay, that's the extended part of the definition, and actually that's how I will cook up this Whittaker, the partial Whittaker corresponding to parabolics. I will impose that some of these maps are 0, some of these maps are isomorphisms. That's how I'm going to replace the non-degeneracy of the characters. So again, the extended part refers that these maps are free to go how they want. If they were all isomorphisms, I would have a twisted version of an n bundle. I have a G bundle with a reduction on U to an n bundle, except it's not an n bundle. An n bundle would be if here I had O, here I just have omega that comes from the fact that I need to do evaluations. So it's a twisted version of an n bundle generically, extended because I just let these maps to be whatever they want to be. I know it's crazy, but
Use a domain, right?
use a domain. It's the same philosophy we did last time. Yeah. Now I'm ready to define the infamous extended Whittaker category, having this pre-stack and having this thing. By the way, I should comment how to form this invariant category. I will comment later if there is interest. Because this is over any power of the curve, this is an in scheme of infinite type.
Nice to explain this for a point instead of
Yeah, I will explain for a point. That's perfect. And then it's easier for me too. It's easier for the audience. All happy. But first, let me define the extended Whittaker category with same notation. So I define it as a fiber product of categories. Smaller. So I start with my D modules on the Grassmannian G run times characters run. And inside that, I have a full subcategory, which is the one I just erased, that I should explain, where I take equivariance with respect to jets against the evaluation. So meromorphic jets run space against the evaluation. That's a full subcategory. And now I wanna get back to Qx, so I'll put it here. And I claim there is a functor that goes from here to here and is moreover fully faithful. What's this functor? It's actually a question for the audience, a flash test. So I claim that, so I define this crazy pre-stack, and now I claim that there is a functor like this. Great, so this functor is a pullback of some maps of pre-stacks. What is it? So again, what I have a G bundle, so a bunch of points, a G bundle, and a trivialization. Let me call it beta trivialization of PG away from those points. That's the Grassmannian part, and then I have a bunch of characters. So eta I, sorry, from where to where? From the, if you want, from the trivial T bundle, so from the trivial bundle to omega, right? And they are also on this space. Is it okay? So that's the first part. And I need to send it to something like that. So I'll send it to the same G bundle. My domain will be this guy. It's actually easy to prove that this is a domain. It's easy to see. And then what I need to have a trivialization, a B reduction of PG on U. Well, then I have a trivialization. I also have a B reduction. Right? So this bundle was trivialized on U. particular be reduced. And since it was trivialized, this guy is the trivial T bundle. I apply the root map, I get the trivial line bundle, and that's my map. So these gamma i's are just these eta i's, and then I moid out. It's a stupid map. It actually turns out to be a quotient. So what I'm doing, what I just erased, I'm doing 2 steps. I'm going down to bundles with generic n reduction, and then I'm modding out by the diagonal action of T on here and on here. It's written in the notes. I think if I explain it, I make a mess. But anyway, this map is.
Can I ask?
Yeah.
You could impose. Could you impose directly the equivariance condition on the domains or not?
On the.
Yeah.
So somewhere I need to go from run to domain. Yeah. And.
You don't have residence, right?
Sorry.
You don't have a residence.
No. I need to work with run, and I could have a category of the run space, but for some purposes that are not inside this lecture but in the conference, it's better to have the reduce to the generic version. That's why I'm doing something extra that complicates the exposition.
I think the question is different, which is can you impose the equivariance condition without saying the words run space at all?
Yeah,
just using Q extended.
Oh, here?
Yeah.
I don't think so.
So can you say it again?
Can we impose
things
just
be done on the left side of the board without looking at the right side of the board, the middle board?
Let me just finish the sentence. Here I pull back, and that the fiber product is by definition the Whittaker category, the extended Whittaker category. Now, what is the question?
What was the question again? The question is, can you define the top left-hand side without ever referring to run space? And I thought you had a complicated way of doing it.
Oh, yeah.
So
Well,
it looks like.
But why would you? Yes.
yes.
But it's a question. It wasn't my question.
So I totally forgot there was a previous version of this definition.
Okay.
Yeah, so before there was a more complicated version to define these Whittaker categories, but this is much more efficient. And yes, you need some kind of, well, some strong approximation in both groups to see that the two are equivalent. But I mean, this is kind of more efficient and more transparent way to define it. So there's no reason to use the
But if you do it naively, just jets acting on that category is invariant.
oh, so jets acting on
Meromorphic jets on,
acting on GUR.
on DQX.
Yeah, that's.
Acting on jets is an option.
You have to put it over the run.
So say it again, just one moment.
So the jets meromorphic, do you have to put them over the rank space? Or
Yes, otherwise where?
Well, you could put it over a single point, but you're only imposing equivariance at that single point. But there
Yeah,
is
but
the whole adelic product of Whittaker.
Oh.
I mean, the little jets automatically
So
What
what he is doing, he's just mimicking what happens in number theory.
Can I?
He's just doing just that. Again, what did you want to say?
I meant to say, you need a version of this back for n, right?
No.
No, well, say so to say. But if you do it generically, you can't really define the residue, right?
So I don't resist the logical status of what you're saying. Are you criticizing what he's doing, or
No, I mean, it's.
are you suggesting an alternative way?
Okay, maybe.
No, but say what you want. Just
It's tutorial after.
I mean, I thought. Well, I wonder if it would be possible to define it directly on this equivariance here without restricting.
where? On fun? On fun engine?
Shifts on QX.
Yes, it is possible. That's how it used to be done. Like if you look at this outline paper, that's how it's done. And what you do.
But you don't have a race. If you have a meromorphic, what I'm saying is that if you have a meromorphic form on a domain,
Yes.
how do you define its residue?
So here's how you do it. I mean, okay. So enough to do the points which are inside the domain. So it's a local version. So it's a local game, and you play, you do Hecke modifications. They're bundled inside the domain. But inside. But again, it's just
Okay.
it's a totally different. It's a totally different way. Give us gives an equivalent definition, but this is much more efficient. So I see no reason to kind of use that one.
There's a notion of good points that are those where you use to impose the.
I think it's very, very confusing. So let's just stick with this because it just mimics number theory and it's just.
Yeah. So I claim that this until here, that's this definition. And next, I have to address the existence of a functor from d modulus on band G to this recently defined category, and to finish, I have to address whether it's injective or whether it's fully faithful or not. So first, how to define the coefficient, extended coefficient functor. Well, what do we have? We have the extended Whittaker category, and so let me write it this way. So you have d modulus on Qx, and I certainly have a map of pullback from d modulus on band G. And I also have a map, so I call this map oblivion because that's what Sam used yesterday. Whenever you have a category, invariant category forgets oblivions to the original category. But I called also that this oblivion, so using notation. So I have an oblivion map to the extended Whittaker. So maybe I got it wrong. No. Sorry, yeah, I got this wrong. So that's an oblivion map, happens to be fully faithful. And that let me just call P. So let me just call P the projection from, I have it here. So P the projection from Qx to band G, the usual stupid projection because my datum starts from a G bundle. And I want a functor of coefficient that goes, extended coefficient that goes from here to here. And to do that, I claim that I have a right adjoint here. I have a right adjoint that in the formalism of SEM, it's called averaging star. And then my functor of coefficient, extended coefficient, will be the composition of pullback from d modulus on band G to this crazy guy, and then do some crazy averaging with respect to the extended character into extended Whittaker. And that's the functor. Okay, and now finally crucial conjecture versus theorems. The crucial conjecture is that for any group, this functor of coefficient x is fully faithful. So that's in contrast with the number theory analogy, where we knew that the function of extended coefficient wasn't injective for some groups. In this case, the conjecture that the team is making, Dima and Dennis are making, is that this functor will be fully faithful for any G. Very conjectural, I guess. Yeah. So then theorem for GLN, this so backwards. It's a conjecture made backwards from a bigger conjecture. And so for GLN, using the mirabolic, like in the number theory case, and some technology of d modulus on infinite dimensional stuff, you repeat the reasoning and you obtain fully faithfulness.
Sorry, so listing y.
Ready?
So
Why you have to believe in it?
yes, y follows from the.
Well, because see, you embed. So say you have geometric Langlands equivalence. So this you embedded this extended Whittaker, and this you embedded some extended version of RevG check. And it's extended version. It's not just RevG check. It's like also generic guys. And that we know is fully faithful. But on the Galois side, we know that the function from integral with singular support into this glued category is fully faithful.
And that we didn't discuss it. Or did we?
No, we didn't. Team will talk tomorrow.
Would this be enough to prove this for customers?
So wait a second, let me just answer. So therefore, like, well, this is an equivalence. This is fully faithful. That got to be fully faithful as well. Pardon me?
Would it be sufficient to prove this for customers?
Yeah. Yeah.
And is it true that faithful? I mean, like, fully faithful is two statements. So
It's one statement.
no, I mean, it's full and faithful, right? So
Well, in derived categories, it's a map of complexes. What do you mean? When do you want to call a map?
if you prove not their object goes to zero.
That's called conservative.
Well, fine. So, but suppose you prove that, would it be?
No.
Would it be enough?
Do you know how to prove that? Oh. Okay.
I can tell you.
Okay, so there is tiny hope. I mean, so my kind of, okay, my tiny hope is that Dima's games with, so, okay, it's also along Roman's lines or whatever, you guys' lines. So this
Yeah,
statement.
that's actually what I meant.
Okay, so,
Yes.
yeah, so like, it's a generic statement. So it's basically kind of, it's only for custodians, some stuff like this. So I hope that, well, something like this. Well, either reduction to P or semi-classical, something kind of semi-classical can do it. So it's like, so the semi-classical doesn't work so well, like around Eisenstein series, but they become very reducible and so on. Like you don't know really how to handle it. But like semi-classical may be pretty good on this kind of part here. Either semi-classical or mod P. So I haven't really thought about it, but like this with way more hope. Dima, what do you say about semi?
Well, first of all, I want to say that anything that's known for arbitrary G is not due to me, or it's not only
For, you mean semi-classical?
yes.
Yeah,
What do you mean semi-classical? I mean semi-classical means quasi-classical. Just Hitchin.
Just Hitchin.
with.
Just
well,
Hitchin.
yeah. Generically, everything is known.
Yeah.
I think just each of them maybe not. No.
Well, that's but yeah.
You want to discuss parabolics?
For me? Because, see, so what's the problem? Functions,
If it's true for categories, then it's
no, that's not entirely true, because see, a function, so you have a sheaf which may not be non-zero, but the corresponding function may be zero over a given function field. That might happen.
I think there's a statement that if you have a stochastic more support of functional field, that if you consider its lifting, it's an extension of your field corresponding to some extension, big extension of the finite field, in its lifting with a more form, then it's supposed to have a non-zero
So there
is no notion of lifting.
Well, I mean, you believe that, I mean, there's no, I mean, you believe that first of all, there should be notion of lifting. So the ones that here, this situation like the, you should think about a situation when the finite fields are algebraically closed.
There is a nice example of this for finite Chevalier groups, but maybe I don't want or for say now of this phenomenon that certain statement that you can state for functions and it's not true for functions, but true for the same image.